again, there's going to be some problems in this section that talk about finding the probability of something happening at least once. And there's a couple things to remember when we say that. When we say the probability of at least once, it means the same thing as one or more. The complement of at least one is none. And I'll work some problems so you can see where we use that, and there's only one way to work those problems. I'll show you some examples in just a second. And then this is kind of the step through for it. I'm going to show you an example rather than just reading through the steps. And then the big thing in this section is what we call the conditional probabilities. We've already talked about it, but now we're going to actually work problems with it. So this is a probability of an event obtained with additional information that some other event has occurred. Remember the problem we did where we took the orders from the table with and without replacement. When we did it without replacement, that second probability was actually a conditional probability. And we write it like this: the probability of the second event given the first event has already occurred. It's called a conditional probability. And there's a couple of ways to look at the formula. I kind of like this one better because it makes more sense. So when you're conditioning on event, whatever you're conditioning on to the right of that little vertical line goes into the denominator. That's kind of your hint. That goes down here. So when we're conditioning, we're only considering the outcomes in the sample space that apply to event A. And of those outcomes, how many of them also apply to event B? And that's what a conditional probability is. We're going to work some problems, again, mostly with tables. And confusion of the inverse. The probability of A given B almost always does not equal the probability of B given A. So you have to read the problem very carefully to see which way you want to do the conditional probability. Okay, so you want to be really careful about that. Okay, so let's do some at least problems first, so I can show you how we work these. So this one is about graduates at a college. A study conducted showed that 57% of the school's graduates find a job in their chosen field within 1 year after graduation. Find the probability that among 9 selected graduates, at least one finds a job in his or her chosen field within a year of graduating. Okay, so the first thing we know is the probability to find a job was given to us to be 0.57. Okay, that was in the problem. What's the probability in 1 year the graduate doesn't find a job? I can use the complement, right? 1 minus the probability of a job, 1 minus 0.57, which is 0.43. Okay, so I know those two probabilities. Now, what I want to find is the probability that at least one of 9 finds a job. Now, when we talk about the at least here, what we're going to do to find the probability is we're going to take 1 minus the probability that none of them got jobs, because this is where the complement rule works. So at least one, the opposite event of that would be that none of those 9 had a job. And I can work this out real easy. Oh, let me go back to my purple pen. So 1 minus, what's the probability the first of those 9 doesn't get a job? 0.43. How about the second one? They're all going to be 0.43. And how many of them were there? 9. Now on your calculator, make sure you know how to do your exponents. So on this little calculator, and I also have a TI-83, I'll show you. So for this one, it'll do order of operations. So I'm going to go 1 minus 0.43. Here's my exponent key right here. Exponent, and I'm going to raise it to the 9th power, and it does the calculation for me. So I get the final answer is 0.999. And then let me show you on the, hopefully mine still has yeah, it does. Okay. Whoops. Okay, let me show you on the TI-83. So on this one, the exponent key is right here, right there. Okay, so I'm going to go 1 minus 0.43. And on this one, when I hit that key, if you notice, it actually goes like a little up caret telling you it's going up to the exponent, put in the 9, and I get the same answer, 0.999. Okay, so it's almost certain that at least one of those 9 is going to get a job. If the probability that any one graduate gets a job is 0.57, if I put 9 of them together, it's almost certain that at least one of them will have a job. All right, let's do another one of an at least. This time we're working with babies in China. So in China, where many couples were allowed to only have one child, the probability of the baby being a boy was 0.545. Among 6 randomly selected births, what's the probability at least one of them is a girl? Okay, so probability of boy, 0.545. So what's the probability of a girl? We're going to assume only 2 outcomes, boy and girl. 1 minus the probability of a boy, so it's going to be 1 minus 0.545, which is 0.1 minus 0.545. What is it? 455. 0.455. Okay, so now I know the probability of a boy and I know the probability of a girl. So I want to know among 6, what's the probability at least one girl among 6 births? 1 minus the probability. What's the opposite event of at least one girl among 6 births? Using the same rationale I used up here. How would I write that in words over here? What's the opposite event? What's the complementary event? Anybody want to try? So if this was at least one finds a job, the complement was no jobs. If this is at least one girl among the births, what's the complement of that going to be?
So it would be 0.4.
No, just word. I don't want numbers, just words.
Oh.
Tell me the words. What would the words be? So this is at least one of 9 finds a job. The complement was none of them find a job. At least one girl among 6 births. The complementary event would be?
Boy.
Right, no girls or all boys. No girls or all boys, yeah. No girls, or same thing as 1 minus the probability of all boys. That's the same thing, right? If there's no girls, that means they're all boys. So this becomes 1 minus, and we know the probability of a boy is 0.545, and we have 6 births. So let's go ahead and do that in our calculator. I'll do it in my TI-30. So I'm going to take 1 minus 0.545, raise it to the 6th power, and I get 0.973. So even though the probability of getting a boy was higher than 50% among 6 births, the probability of getting at least one girl was pretty high, 0.973. Okay. All right, let's do some conditional probabilities from tables, because this is usually where you're going to see these. So this is a little table. It shows you all passengers, airline passengers must pass through security screenings, but some are subjected to additional searches. Travelers who carry laptops wonder if that makes them more likely to be searched. So we have data here for 420 passengers aboard a cross-country flight, and we have them whether or not they had a laptop and then whether or not they had that additional search. So the first question is, if a passenger is randomly selected, what's the probability they'll be subjected to an additional search? So what's the probability based on that table of an additional search? So there's 420 passengers. How many of those had an additional search? What number is going to go in my numerator?
175?
Yes. 175 of them. And let's see. The decimal for that is, let me look at my notes, 0.417. Okay, now, if a passenger has a laptop, what's the probability they'll be subjected to an additional search? This is a conditional probability. We're only looking at the people with laptops. So the probability of a search given they have a laptop. Okay, so how many people in that table have a laptop?
72.
72. And how many of those people were searched? Just looking at that row, how many were searched? 30.
30.
Yep. And if you divide that, you get the same answer. So what does that tell us? It tells us the probability of being searched does not change given we have a laptop. It's still about 42%, which tells us that actually these two events are independent. The idea that you have a laptop subjected you to a more likely to have the additional search is not supported by the data in this table, because 42% of all people were searched and 42% of people with laptops were searched. If you do the same thing for this row here, if you take 145 and divide it by 348, you'll also get 0.417. So the answer to the last part of the question here is no. Passengers with laptops are not more likely to be subjected to the additional search. So that's a nice use of conditional probability. How are we doing? Let's see, how much time do we have left? Okay, I guess we have time. I have two more examples. The last one I really want to do, this one's a quickie. We'll do this one real quick. This one's about results of head-on collisions of passenger cars and whether or not the person used a seatbelt and whether or not they were killed. So let me put the totals down because I didn't give you those. So this is 10,660, 7,442, 8,057, 10045, and then the total in my table is 18,102. Okay, so if a driver is randomly selected, find the probability that the driver was killed. So probability killed. Okay, so we're going to take all the people in the table, that's the denominator, and how many of those 18,102 were killed? 8,057. Okay, straightforward probability right off of the table, not hard. And the decimal is 0.445. Now, let's take a look at what the seatbelt does, whether or not it changes the probability of being killed. So if we select one driver at random, find the probability they were killed given they were using a seatbelt. So probability of killed given they used a seatbelt. Okay, so now we're just going to use the people that used a seatbelt, which is the first row. And there's 10,660. And how many of those were killed? 3655. Oops. 3665. Yeah, that's right. And if I divide it, I get 0.343. So what do I notice now? So the overall probability of being killed was about 45% from this data. If the person was wearing a seatbelt, the probability of being killed has dropped down to 34%. Now let's do the other one. Let's do the probability of being killed given no seatbelt. Okay, so now we're talking about the no seatbelt people, and there were 7,442 of them. And how many of them were killed? 4,402. And if you get the decimal on that one, you get 0.592. Okay, so what does this tell us? Does the data suggest that a seatbelt affects the likelihood of the driver being killed? What do you think?
Yes.
Yes, it does, right? Because it went from 45% overall, and then we jump up to almost 60% if they didn't use a seatbelt. So yes, the answer here is yes, definitely. Unlike the one we just did where there was no effect about the searches and the laptops. Okay, one more example. This one I really like because it's a true story. So, oh, I don't have my, hold on just a second. I'm trying to find my sheet with all the totals on it. I don't see it. I might have to do these by hand. Seatbelt. Nope. Okay, I'll have to do these by hand. I don't have my answer key for this one. Okay. All right, so this is a true story. I know some of you want to go into nursing or already in nursing. So alert nurses at the Veterans Affairs Medical Center in Northampton, Massachusetts noticed an unusually high number of deaths at times when another nurse, Kristen Gilbert, was working. The same nurses later noticed missing supplies of the drug epinephrine, which is a synthetic adrenaline that stimulates the heart. Kristen Gilbert was arrested and charged with 4 counts of murder and 2 counts of attempted murder. When seeking a grand jury indictment, the prosecutors presented provided a key piece of evidence consisting of the table below. So the table shows the shifts when Gilbert was working and when she wasn't working, and then whether or not the shift had a death or no death. And I need my totals. So let me just put these in real quick because you're going to need these to work the problem. 217 plus 1350. Oops, 217 plus 50. Oh, 1567. And this will be 257. 34 plus 1350. Plus 257. 1641. And let's just make sure we got the right total. 74 plus 1567. Okay. All right. So I just put the totals in. So overall, what's the probability of having a shift with a death? So of all those shifts in the table, and there were a total of 1,641, how many of them had a death? 74. So let's figure out what the decimal is. 0.045. So a little bit more than 4% of the shifts had a death. What's the probability of having a shift with a death given Gilbert was working? So this is probability of death given Gilbert working. So now we're just going to worry about the shifts where Gilbert was working. And we have 257 of those. And how many of those had a death? 40. So now if I take 40 and I divide by 257, I get 0.156. And then what was the probability of having a shift with a death given Gilbert was not working? So probability of death given no Gilbert, let's put it that way. Okay, so the shifts where she wasn't working were 1384. And how many deaths do we have? 34. So if we take 34 and divide by 1384, we get 0.025. Okay, so what does this tell us? So overall, about 4.5% of the shifts had a death. When Kristen Gilbert was working, that went up to over 15% of the shifts having a death. When she wasn't working, it dropped down to 2.5%. What does that tell us? Do you think this provides support for the grand jury to support the charges against Gilbert?
Absolutely.
Absolutely. She's in jail, actually. This happened back in the 1980s in Massachusetts, and she was convicted. But it's a real world example where, you know, with a simple little data table like that, and you can't see that relationship unless you start to look at the conditional probabilities. It just doesn't jump out at you otherwise. But they use this table actually to present to the grand jury for the indictment, and she was convicted. And I believe she's still alive. She's probably in her 70s by now, but I believe she's still alive and in jail and in prison in Massachusetts. So I'd like to finish up with that example because this is real world data. So gives you an idea of how conditional probabilities are used. All right, so let's just pull up your homework real quick. I believe we've gone over everything that you're going to see in your homework. Let's see. Should take us over there. There we go. All right, so this is chapter 4. Let's go back out here, assignments. So there's 3 sections that we cover in chapter 4, which is 4.1, 4.2, and 4.3 that we did today. There's not a lot of homework problems in here because we just really don't do that much probability anymore in the stats class. So here's a probability. You know, it says it's impossible to get 10 kings. Express this as a probability number between 0 and 1. That's a pretty easy question. That's one with a conclusion like we did a couple examples of those. Same thing on this one, there's a conclusion one. Okay, and then this is one where they give you the number of boys and the number of girls, and they want to know what's the probability of a girl using that technique, and then does it appear to be effective in increasing the likelihood that the baby will be a girl? And you just do some simple calculations on that one. Here's one here about peas. So I don't think you're going to have any trouble with these. Yeah, these are all pretty straightforward. The ones I think might be more difficult, we get into 4.2. 4.3, I think they gave you the tables. Let's take a look at 4.2. Oops, 4.2. No stat crunch in this section, by the way. You don't need any stat crunch on these. You will need your calculator, though. That's a definition question. Definition question. Definition question. Definition question. Okay, that's just interpret there. Okay, here's one where the table's given to you. Again, notice you're going to have to add up. This is just like the one we did. Order accurate, except they don't have names of restaurants here, but you're going to need the totals, the row totals, column totals, and overall total to answer the question. So you will have to do those on a piece of paper. Same thing on that one. This is the one where you're going to say, where it says hint, create a table. So this is just like the example I did for the prostate cancer and the positive and negative test results. Exactly the same setup with different numbers. So you know how to do that. That's why I did that example for you. Same thing on that one. And then there's another one with a table that's already made up. Yeah, so I don't think you'll have any trouble with those. And then, let's see if we can get back to 4.3. 4.3. Oh yeah, he does this weird thing in here with this money stuff. I don't really get this, but okay, so here's one of the at least problems like I did with you about getting a boy or a girl. So you know how to do those. And then here's one with a table. And again, you're going to have to do your row and column totals here. And then they're going to ask you some questions based on the data in the table. So we did examples just like that. Just a different scenario in the table, but you'll be fine on these. The same thing here. Here's one about the positive and negative test results. Yep, that's it. So you don't have that many problems actually in your homework for this section. No stat crunch. You don't need stat crunch on this unit, on this part of the unit. Next week we will use stat crunch again, but this week you don't need stat crunch. All right, so let me stop here, see if there's any questions. So we did all probability today. So 3 sections. And again, don't forget you have 3.1 to 3.3 due tonight along with the unit 2 test. And also, I also did send reminders out to people. Let's go back here just for a second. To get your honor lock sample test done. So let me go as a student here. I can't see honor lock like you see it, so I can't really demonstrate it for you up here, but on your top toolbar, I think yours is up there already. There is a link to honor lock. You need to take that sample test. All right, and you have to do it using this honor lock link here. If you look on your assignment page in my stat lab, it sits here, okay? Before you go through the honor lock, set it up over here, okay, in another window. So when it comes the right time when you're in honor lock, it'll be ready for honor lock to enter the password. But you have to do your...
So do we have to type any password in it?
No, honor lock will put the password in for you.
Okay.
Honor lock will do it. You do your ID check, your room scan. After that, your picture will be up there. And underneath your picture, it says insert password. You have to click that button in honor lock and you'll see the password go in. I have a video here. If you've never done this before, there's a video in the honor lock information module right here. There's a quick little video that shows you what happens when you do that. I also opened up your midterm exam materials module. You want to take a look at that. And once you finish the honor lock sample test, you will have access to the midterm preparation quiz. But you see there's a little flag there and you can't get that unless you do the honor lock sample test. But the preparation quiz, and in 2 weeks, we'll go over a copy of that in class to get you ready for the midterm. This will help you get ready for the midterm, but you need to do that sample test, that honor lock sample test before you can access this. So that's why I was writing and writing to you about it. I think I sent yours on Sunday or Monday. Well, today's Monday. I think I sent yours yesterday, telling students who hadn't done it yet, they need to get it done. Because then you'll have access to this preparation quiz, which you can take over and over again to help you get ready to take the midterm. Okay? So you need to do that honor lock sample test. If you have trouble while you're trying to do it, there's help available in honor lock. Please click on that live chat option. They'll come in and help you. I can't help you. I'm not part of their system. The people that are in honor lock can help you though, and they're really good about jumping in and helping you if there's a problem. All right. You have to do that sample test, no exceptions. Everybody has to do it. It doesn't count towards your grade, but you need to do it in order to unlock the prep quiz and also the midterm. Okay, questions? So we're almost halfway done. Anybody have questions? And as we're finishing up, let me go back and stop. We don't need to record anymore, I don't think. Stop recording. Yes.